Cool. Yep. You know what, actually, we're going to go with no rule lines because here's what we're going to do. I'm going to do a concept map. All right. This is the invertible. If you want to see all the statements of the invertible matrix theorem, like the following are equivalent, right? It's exactly like how it starts with the invertible matrix theorem. You can go look at it in your book. What I want to do is draw connections. I think that's actually going to make a difference. So I'm going to actually create a concept map. So this is the IMT. So we're going to start out with let A be square. So A has to be square. It's a square matrix. Okay. And in the world of matrices, what we've done thus far, all right, we've got, on the one hand, we've got systems, right? And these systems are those of the form AX equals B. And then we have sets of vectors. And that's V1, V2, all the way up through Vn. Like that. Okay? And at first, they don't seem related. Okay? At first, they just don't seem related. So we'll start out with some of our ideas of sets of vectors, and we start out with this idea of span. Okay? We've got the idea of span. And we're going to look at the span of V1, V2, all the way up through Vn. Okay? We got that idea of span. Okay? And the idea here is that a vector is in the span if we can write it as a linear combination of the other vectors, right? That's the idea of span. And that's going to relate to systems in the invertible matrix theorem, okay? And by the way, this is only for the IMT. So we want when A is square, okay? That's going to relate to when AX equals B, right? Notice B not 0, or well, actually it's in 0. AX equals B has a unique solution for all B in Rn. So that's how they're tied. They're tied together that way. They go back and forth with one another. So span has to do with the idea that we have vectors and we can construct a space using the vectors, okay? And by the way, we should say the span of them equals Rn. So I add that little piece there. Next up, we got this idea, right? Okay. That the set V1, V2 through Vn is linearly independent. So the set V1 through Vn is linearly independent. That's our next idea. And if we look at our systems, that's going to correspond to this statement here. The only solution to AX equals 0 is the trivial solution. So they're connected, right? If we want to prove linear independence and if we want to prove linear independence, we show that the only solution to AX equals 0 is the trivial solution. So those two are connected. Now, let's think about this for a second. Let's say, for example, any questions on that? Like all we're doing is we're just connecting some of the different ideas. We've got this set of vectors, v1 through vn. And if we have the set is linearly independent, then that also means that the only solution to AX equals 0 is the trivial solution. That's that connection that we get between the theorems. If we know that the span of v1 through vn equals Rn, then we know AX equals b has a unique solution for all b belonging to Rn. Okay, here's the next one. What I want to do, what if I know, okay, so these are the two things that I know. I'm going to highlight them now in yellow. We're going to get something as a result of them. All right, and we want to draw a relationship here between the two. So I've got, we know that the span v1 through vn is Rn, and v1 through vn is linearly independent. What do we get as a result of those two things being true?
Basis?
Yeah, exactly. Okay, a basis for what? We want to say what it's a basis for, because it's got to give us a basis for the space con. So v1, v2 through vn is a basis for what?
For Rn?
That's exactly right. So it's a basis for Rn. Very nice. So when we have span and linear independence and dependence, or linear independence, we get a basis, and a basis specifically for Rn. Very nice. Good. All right, now I've got a third idea that I'm going to work with here. So can you guys see, those are the relationships that we've been working with thus far. We've connected span to AX equals B and the solution for all B. We've connected the set V1 through Vn is linearly independent to AX equals 0 has only the trivial solution. And then we know that if we have the set spans, this set V1 through Vn spans, and then V1 through Vn is a basis for Rn, V1 through Vn is linearly independent, we get a basis for Rn. All right. I should add a little piece of information just so that just in case it's not clear, there are n vectors in the set. Hence why the V1 through Vn. But there are n vectors in this set, and that's actually, if you remember, really important. So now I've got another idea that I'm going to add to this. All right. Oh, I'm going to kind of think about how I'm going to kick things. Okay. So this is now the matrix A. All right, and I'm actually going to write it out a little bit. Or should I put it off to the side, or should I put it down below? What do you think? The side or down below? Where should the matrix A go? Side or down? Good question, right? Okay, well, let's put it down. Nobody has an opinion. All right, so when we talk about the matrix A, all right, let's do a couple things that we need to make sure that we understand what A is. So A, right, A equals the matrix of the column vectors. So it's going to be V1, V2, all the way up through Vn. So it's the matrix of the column vectors. All right. So what we need to do now is we need to now connect the stuff that we know about A, right, to our ideas in systems, and also when it comes to vectors. So we got A, the matrix of the column vectors. All right, we got it's square. Okay, we know that already because we said A is square. All right, how about we start with this one? We're going to start out with the null space of A equals 0. What should I connect the null space of A equals 0 to? Think about that. What does it mean to be a null space? What should I connect it to? Which one of the ideas? I don't want to make it too small, but which one of these ideas should I match up the null space of A equals? Yeah, okay, we could definitely do it with the trivial solution. Very nice. That's it. So the only solution to AX equals 0 is the trivial solution. What's the trivial solution? The trivial solution is the 0 vector, right? And the null space is the set of all solutions to AX equals 0. Right? And if we want to connect some things together, which we do, because we want to connect them inside of our minds as we're working, let's make these blue ones. Their blue ones are all connected together too. One, linear independence. Like we said, we match that up to the only solution to AX equals 0 is the trivial solution. And then that also matches up with the null space of A equals 0. So we know any one of those, we know all three of them. They're basically equivalent, just in different situations. Okay. Now we have the call space of A equals Rn. So the call space of A equals Rn. We want to think, what is that related to? Call space of A equals Rn. Make that one pink. Which of our other ones instead of our concept map is that one going to be related to? Because it is. Remember that the call space is the span of the column vectors of A. Which one might it be related to? So if you think the definition of the call space of A is that it's the span of the column vectors of A. What are the column vectors of A? Do you know what I mean when I say column vectors of A? It's impossible. No, of course you do. Maybe not. I don't know. It's a good question. What do you think, Daniel? If the column space of A equals Rn, and what it means to be the call space of A is the span of the column vectors of A, which one of these up here matches up with that call space of A equals Rn?
Yeah, would it be the span of the v1, v2 through vn equal Rn?
Yeah. Now, if you notice, the column vectors of A are v1 through vn. Right? If you look at A, how we constructed A is constructed as v1 through vn. The column vectors in A are v1 through vn. So the span of the column vectors of A, that's that one right there. Okay. Those are equivalent statements. There we go. And then, like we said, AX equals B has a unique solution for all B. Boom. There we go. That's it. Span. Way to go, Con. So we got our big ideas, sets of vectors, right? This matrix A systems, right? Okay. Next question. All right, so this is the invertible matrix theorem. So we've got some other statements in that IMT, right? Other statements in the IMT? Like, what's another statement in the IMT?
Professor, can I ask?
Yeah, what's up?
So for the null, from the matrix, we have the equivalent that null space equals 0, which means that AX equals 0 is a trivial solution, and that span is linearly independent. So isn't that from these two, like these two blue, like circle, we can have the other, so isn't that they're all equivalent? You mean,
They
do you
will be all
understand what I
equivalent.
mean? Yeah.
Yes, they're all equivalent if A is square,
Oh, okay, yeah, got that. I just always
right?
forget. Yeah.
Yeah, so that's really important. We'll see some examples here as we review where we get non-square matrices. But here's the deal. Here's the thing. You see all the blue ones? The blue ones are equivalent whether or not A is square or not. Okay, so like, for example, the call space of A is Rn. Well, that's going to be equivalent to V1 through Vn is linearly independent if the matrix is square. But if the matrix is not square, they're not equivalent. But the three blue ones, null space of A equals 0. The only solution to AX equals 0 is the trivial solution. And V1 through Vn is linearly independent. They are equivalent no matter what. Does that make sense?
Yes, it does. Thank you.
Yeah, and that's the whole idea. We're trying to like bring some key ideas together from the entire chapter. Okay. All right. What else do we know about the matrix? We've got a square matrix. We're going to say, like, you know, the only solution to AX equals 0 is the trivial solution. What's another thing that I know? What about the determinant, Con? That's right. Okay. You got the determinant of A. What about it? It's non-zero. Yes? So the determinant of A is non-zero. And like you said, A is invertible. That's right. A is invertible. Yes? That's another equivalent statement if A is square. All right, this is more stuff about we know about A. Big things that we need to know. Here's another one. Okay. The nullity of A equals 0. You guys remember what the nullity is? What's the nullity?
The dimensions of the null space of A.
It's the dimensions of the null space of A. So it goes along with that null space, right? At the null space, the only way that you get a zero-dimensional null space is if the only thing in it is the zero vector. Okay, there we go. And so that nullity of A is also equivalent to those other statements about linear independence, linear dependence, okay, and AX equals 0 being the only solution to AX equals 0. Excuse me. There you go. And for my purposes, let's see, is there anything else I want to throw in there? Oh, we got a big one. Got a big one. Has to do something with the matrix. We got two big ones. You want to prove, let's say we want to prove A is invertible. How do you go prove A is invertible? How do you guys prove A is invertible? Yeah. Think about it. Yeah, okay, that's it. The RREF of A is equal to the identity, equals I3. Or IN, excuse me, is the identity, right? It row reduces the identity. That's it. Are there any others? There's one more.
Is it the rank of A being n?
It's the rank of A equals N. Yeah. The rank of A equals N. By the way, which only works if A is square. So the rank of A is equal to N. There we go. You can kind of connect determinant of A being non-zero to having, you know what? I don't. These two kind of connect in some ways. Certainly these two connect, right? But they connect via A, right? You row reduce down to identity, you get the rank of A equaling N. Anybody else see any other ones that connect? I think maybe if we think about A being invertible, we can have X equals A inverse B. That'll solve our systems, right? In some ways, that's kind of related too. So if you think, I'll write that down. So we can connect. Oh, it's getting big, eh? So A being invertible and AX equals B having a unique solution for all B. Remember, they're connected by X equals A inverse B. That is that you take the inverse of A multiplied by B. Oh, great. Nice, Con. That's something to definitely think about. That's right. So we've got that connection between A is invertible and X equals A inverse B. And then exactly like you said, we also have the row space of A equals Rn. And that actually kind of goes along a bit with the span idea too. Not as directly as the call space one, but pretty connected. Those two are very connected. So in our invertible matrix theorem, okay, we've got on page, now, so this is actually just designed to kind of help you envision the connections between a lot of the things that we've got going on. So span is going to be connected to AX equals B, having a unique solution for all B belonging to Rn, right? In fact, we're going to use this thing here in order to prove span. If the call space of A is Rn, that's also going to prove that the set of vectors span Rn. Okay, that's going to work. The row space is not going to be the same exact thing, right? So maybe I shouldn't have it be pink. It's okay. But it is connected to the column space because we kind of find them similarly. Okay. The blue ones, they're all connected to linear independence and that idea of linear independence and linear dependence. Okay, so if we know linear independence, we know all these guys here. Okay, right? And so that's kind of one of those connections. Now, the other thing that we have here, we have one more other connection that I want to highlight, and we'll make this one green, is if we get span, we take span and we add to it linear independence for a set of vectors, we get a basis. Take span plus linear independence and you get a basis. Pretty colorful, eh? All right. Any questions about the setup of the concept map? Just trying to connect some things, you guys. Like theorems are the hard part, right? How do I connect like abstract ideas? Well, maybe this might help. We'll see. So let's take 5. It's 6:30 now. Please come back at 6:35, and then we're going to use this. Okay. All right, come on back in. So let's take a look and let's use this a little bit. Let's use this. Is the set, okay? -1, 2, 1, 1, 3, 0, -1, 3, 2, 1, 2, 2, 0, -1, 3, 1. Linearly independent. Is that set linearly independent? Why or why not? How do you know? All right. Yep. So you go do that, Con. We're gonna practice, make sure that everybody can actually use their calculators. And they can set up everything correctly. When you're done, tell me yes or no. Put it up in the chat. Also, as you're working, work on your explanation. Right? Once you figured it out, yes. Tell me, how would you explain it to me? Is the set linearly independent? How would you know? Okay. It needs a little bit more than that. But good. It's a good start. You just need to give me the theorem, Colin. The set isn't trivial, Jorge. What about it is trivial, right? Okay. So we don't say the set is trivial. Yeah, that's it. So go up, you can actually look at it like at our concept map, right? The only solution to ax equals 0 is the trivial solution. What do you think, Doc?
Since the trivial solution is the only solution, the rank of A must equal to n.
Uh-huh.
And since the rank of A equals to n, A is invertible. Wait, actually, do I need to know that A is invertible? I don't
Not
think so.
necessarily.
I just need to check if what's the determinant, right?
Okay, so first, how did you figure out that ax equals 0 has only the trivial solution? Let's start with that.
Oh, wasn't it? I thought it was given.
No,
Oh, okay, sorry.
here's the set. Yeah, we just want to figure out, is that set linearly independent? Jorge said that, in fact, yes, that the only solution was the trivial solution to ax equals 0. How'd you find that out, Jorge? Okay, go ahead. I mean,
The reduced row echelon form, and it became identity I sub 4.
okay, so A, first we actually got to show A, right? Okay, so A equals -1, 2, 1, 1, 3, 0, -1, 3, 2, 1, 1, 2, 1, 2, 2, and 0, -1, 0, -1, 3, 1. Okay, great. So you're like, okay, there's A. A is the matrix of column vectors. You constructed that. What's next? All right. Oh,
I put in the calculator, so then
that's great.
it came out with the what is it 1 0 0 0.
Yeah. You came
And
up
then-
with the identity, right? All right. Now, a lot of ways we can skin this cat. It's a terrible saying. It's a terrible saying because nobody skins cats. Freaking terrible. Don't do that. Don't skin a cat. All right. So once I've gotten here, how do I show that the set is linearly independent?
Would it make sense to say yes, because RREF of A is equal to I sub 4, So AX equals 0 has only the trivial solution by IMT, which means the set is linearly independent.
Okay, so absolutely true. We could totally do that. Now, here's a couple of things. One thing to get here. So if I get a matrix that looks like this, not just the identity, but in fact, one in which I have a pivot in every row, excuse me, a pivot in every column. So I've got a pivot in every column, right? So AX equals 0 has only the trivial solution. That's very true. And then if I say that, okay, like that proves it. Pivot in every column, only the trivial solution. So the set is linearly independent. You actually don't even need to say by the IMT. And the reason why you don't need to say by the IMT is because these two are always equivalent. AX equals 0 is only the trivial solution, and the set is linearly independent, always equivalent. Or, okay, or we could skip the AX equals 0 has only the trivial solution. Because we have A, so we wrote A, okay? A is square. Everybody see that? The RREF of A equals I4. So the set is linearly independent by the IMT. And that, by the way, is only if you need to justify. But let's take a look at what the difference is, okay? And this has to do with, this is math. I mean, this is how math kind of rolls, okay? So on the one hand, we prove AX equals 0 has only the trivial solution by taking the row reduction. And you're basically ending up with x1 equals 0, x2 equals 0, x3 equals 0, x4 equals 0, right? That's what that thing right there says. So AX equals 0 has only the trivial solution. It says that whether or not it's square or not, if you have something that looks like this, ones and all zeros, okay? So if we have AX equals 0 has only the trivial solution, the set is linearly independent. Those two are equivalent. You don't need squareness to have those two be true. Or another explanation is to just skip the AX equals 0 is only the trivial solution, because once A is square, right? Remember how this works. The invertible matrix theorem says if one is true, all are true. You guys remember that? The IMT says if one is true, all are true. So I get the RREF of I equals IN, then all of these are true, including V1 through Vn is linearly independent. So all you need is the two conditions for the two conditions that you got from the IMT. A is square, and it row reduces the identity. And that gives you linear independence by the IMT. I should add that. Oh, I did by the IMT. There you go.
So just to clarify, the whole flow chart that we did up top, everything under that is encompassed under the IMT.
Everything under there is encompassed in the IMT. So if A is square, they're all true.
Got you. Thank you.
You're welcome. Finish the sentence, Daniel. If one of them is false,
then they're all false.
That's right. That's the IMT. Yep. A is square. So if one of them is true, they are all true. If one of them is false, they are all false. Now you want to practice what it means for them to be false, right? Like AX equals 0. The opposite of AX equals 0 is only the trivial solution is what?
Sorry, you said the opposite of having only the trivial solution?
Yep.
You would have some type of free variable or like a column with, you'd have infinite solutions.
There you go. You'd have infinite solutions to AX equals 0. That's right. Yeah. Okay. That's for AX equals 0. Okay, good. Okay, let's try this one. All right. let S equal 1, -1, 2, 2, -2, 4, 3, 0, 1. Does the set span R3? So does this set span R3? And how do you know?
Would it be well, so first I drew A out, or I drew out the matrix A and then did the reduced row echelon form.
Mm-hmm.
And with doing the reduced row echelon form, you only have 2 pivots, so then that would mean it couldn't span R3 because you don't have enough vectors.
What was your RREF of A?
It is 1, 2, 0,
Mhm.
0, 0, 1, and then a 0 row at the bottom.
Okay. All right. So tell me how you're thinking.
So since you only have 2 rows with or 2 columns rather with pivots, you'd only have 2 solutions, or 2 vectors rather. So you wouldn't have basically the second column is linearly dependent. So you don't have enough to get you R3.
That's great. That's absolutely true. Totally true. Okay. So we look at this and we go, okay, well, the second column, right? The second column is in fact 2 times the first. True? Yep. So they're scalar multiples of each other. And so only the first and the third column constitute a linearly independent set. 3 columns together are linearly independent, right? So we only have a plane. We're going to 2-dimensional space in R3. Okay, great. That's perfect. Right. So one way to write this is to say, right, since there is no pivot for, and you can call it X2 or C2, whichever one you call it. It's like that they're, you don't have to say both. You can say one or the other. This means that the second vector, right, okay, forms a linearly dependent set. Or the second vector actually, okay, is not necessary for the span, because that's what we're really asking. And so the first and third vectors form a 2D subspace of R3. and not all of R3. R3 needs 3 of them. So that's one way to think about it. Absolutely. Any other ways that I would go through and prove something like this? What do you think, Fung? How would you state that, in fact, no, the set will not span R3?
I want to tap, but I hear that there no explained for you already, so I just stop.
Yeah, you're thinking the same thing?
Yeah, I think the same thing.
All right, cool. Anybody else? Good. I'm actually really happy because that's actually another piece that we really want to get at. We want to get at that if I'm missing a pivot, that one that misses the pivot, right? It's going to form the 2 vectors here. They actually form the call space of A, right? Because you're going to go back 1, -1, 2, 3, 0, 1. They form the call space. That's how we find a call space. And so that call space only has 2 vectors in it. So it's a 2D subspace of R3. Now, here's the thing. I can also write it like this. RREF of A does not equal I3. So the set does not span R3. By what?
By the IMT.
By the IMT. That's right, because we have a square matrix again. There we are. Well, actually, I said A is square. We'll add that to the front. REF of A does not equal I3, so the set does not span R3 by the IMT. There are a lot of different theorems that you can use here that work, right? Like the rank of A, it's not N. The rank of A isn't N. If you remember from the first one, right? AX equals B cannot have a unique solution, or doesn't necessarily have solutions for all B. So it's not going to span. Okay. Questions on that? All right, let's try another one. Shall we? We shall. Okay. How about this? Suppose the determinant of A equals 7. Do the column vectors, determinant of A equals 7, and A is 5 by 5. Do the column vectors of A form a basis for R5? Look at your concept map. Okay. Question is, why would you say no? Fool.
Would it be yes, because the determinant of A does not equal 0? Well, A is square, the determinant of A does not equal 0, and thus by IMT, the column vectors form a basis for R5.
Okay. How do you know it's R5?
Because N is equal to 5. Well, it's 5 by 5, so.
5 by 5. Yeah. That's the only other little piece there. By the way, if you have a determinant, you don't even need to say that it's square. You can't get a determinant for a non-square matrix anyways, so There it is. Yeah. So we got a squared. It's good habit. All right. The determinant of a does not equal 0. And the column vectors of a are in R5 because it's 5 by 5. So the column vectors form a basis for R5. Column vectors of A form a basis for R5. By the IMT. Excellent. Good. Okay. So now let's take a look. So let's do we're got a different, what's something different here. Okay. So let's say, for example, so we'll let S will be our set of vectors. Okay. So we'll let S equal 1, -1, 2, 2, 1, 3, -1, 1, 2, 1, 0, 2. Okay, 2, 1, 0, 2. We're going to answer some questions about this set of vectors. One, are the vectors, is S linearly independent? Two, do the vectors of S span R3 or R4? Excuse me. Three, do the vectors form a basis for R4? Four, what is the null space of A? Five, what is the row space of A? Six, what is the call space of A? What is a geometric description of the call space of A, row space of A, and null space of A? Eight, what is the nullity of A? And then 9, use rank nullity or confirm rank nullity using it. All right. So we are going to take 5 minutes now, or 6 minutes. We're going to go till 7:10 on a break. When we come back in, okay, I'm going to take you to breakout rooms. So you're going to have a group of 3 students in each room, and you're going to work through something like this, okay, together. Then we'll come back together again. I'm going to pop in, right? And if you're after about 5 minutes or so, that way you can kind of like work through it a little bit. And if you're silent, I'm going to ask people questions randomly. And it may have nothing to do with linear algebra. It may be all physics questions. And nobody's going to want that. That's horrible. So you should be talking with one another. You got that? Okay. So let's take 5, be back at 7:10, and then I'm putting you in breakout rooms. Okay. All right, come on back in. The point here is to, okay, so we're gonna go in. Everybody's got everything that's all written down, I hope. And what we'll do is like, I'll set it up. I'll come on in about 5 minutes or so, maybe a little bit longer. If you want, you can go in and separate out the questions into pieces, right? Or you can go through and be like, okay, here's how we're gonna approach it and do it all together. It's completely up to you. How do you want to do it? Okay. So I'll be in, I'll be right here if you do have any questions. So I'm just gonna, let me send you to your breakout rooms. All right. There we go. Okay. Sign automatically. And so it'll open the rooms and go on in once you've gone in. Okay. You should now get an invitation. Cool. There we are. All right, Davis. All right, Anas. Head on in. You guys there? So we've got this, right? We've got an S. Is the set S linearly independent? What do you think, Miguel? Is the set S linearly independent? And how do you know?
That would be a yes, right?
Okay, yep. And how do you know?
Since no, give me a second. Since zero vector would be the only trivial solution, right?
Since the only solution to AX equals 0 is the trivial solution, yes.
Yeah.
There you go. How did you know that the only solution is AX equals 0?
Off
Sorry.
our
Go on.
it would be off the reduced echelon form, right?
Okay, great.
Yeah.
And when you looked at the reduced echelon form, was there anything that told you, yes, this is going to give it to me?
Well, I mean, it was almost an identity vector except for the last row, which is 0.
Okay.
Yeah, so.
If I look at this, okay, great. I'll let you turn off your mic. All right, cool. So if I look at an adjoint matrix, right? 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. So what I heard, everybody, row reduced their matrix, and that's the solution to AX equals 0. Right there, you adjoin you augment with the zeros, and what you get here is, if we rewrite that, that's X equals, right, 0, 0, 0. And so the only solution to AX equals 0 is the 0 vector, hence the set is linearly independent. And you can go like, look, there. It's the only solution. Do the vectors span R4? What do you think, Davis? Do the vectors span R4?
No.
How do you know?
So we only have 3 vectors, so we don't have enough dimensions to expand to R4.
Exactly. Perfect. Good. Not enough vectors. All right. How about 3? Do the vectors form a basis for R4? What do you think, Jorge? The vectors form a basis for R4?
No, because there's not enough vectors.
There's not, okay, there's not enough vectors. That's right. Good. Okay. Or the vectors do not span R4. In order to have a basis, we need the vectors to span the space. And they don't. Good. All right, Daniel, what's the null space of A?
Equal to the 0 vector, because the only solution to the oh gosh, I'm blanking on it, but the only solution is the 0 vector.
To AX
The
equals
identity
0
matrix.
or the homogeneous
Or-
system? Yeah, sorry.
Yeah. No, yeah, you're good.
Okay. Good,
Under the 0
excellent.
vector.
What is the row space of A? What is the row space of A? What's the row space of A, Con?
Row space of A, it's the first 3 rows of RAF,
Okay.
and it's
So what are the-
R3.
So that's what?
So it's 1 0 0 0 1 0 0 0. No. So if it's vector, it's gonna be yeah. It's true. Yeah.
Like
So
that?
1 0 0 0 1 0. Yeah.
So it's the span of those 3 vectors. What do we call that? There's another name for it.
3.
It's R3. Yeah. In fact, the row space is R3. Now, Larry and Con and I and Fug and I were talking about the fact that like these vectors, the 3 column vectors are not a basis for R3. And that's true. But the 3 row vectors are. You see that? Because they're in R3. There's 3 linearly independent vectors in R3. 1 0 0, 0 1 0, and 0 0 1. So the geometric description for the row space is R3. Okay. What about the call space of A? What is the call space of A? By the way, does that make sense? 3 linearly independent vectors in R3, that's R3.
Yeah, I had a question about that, so thanks
Sure.
for clarifying.
Okay, cool. What's the call space of A? What's the call space of A here, Phung?
For me, that is R3. And I write it down. That's a the column
Okay,
of A. That is -1, 2. Wait. That is 1, -1, 2, 2,
uh-huh,
and then 1, 3, -1, 1, and the next one is 2, 1, 0, 2.
excellent.
R3.
That's right.
Yeah, R3.
It's all three of them, right? That's gonna be the call space of A. Okay, all right. Now, what is a geometric description now of that call space? How do we describe that geometrically, Phung? Right there, Con. There's the call space. That's the basis for the call space. Right? We've got a pivot in every single one of the columns. And so consequently, what we end up with is that all those vectors, that's the call space. So the call space of A, we can write it as the span of 1, -1, 2, 2, comma 1, 3, -1, 1, comma 2, 1, 0, 2. And that's the call space. How do we describe it geometrically, Juan? What is the call space geometrically?
Is it a three-dimensional plane?
It's a three-dimensional, and that would be actually what's called a volume. If it's got
Volume,
three
yeah.
dimensions.
Three-dimensional, yeah, volume.
Okay, in what space is it in? It's a three-dimensional, and we call it a three-dimensional subspace of what? Right, so we want to be complete with this as a 3D subspace of R4. The vectors are in R4, so it's going to be a subspace of R4. What's a geometric description of the row space? What is it, Daniel?
The row space is just R3 would be a volume in R3.
It's all of R3. You don't even need to say that it's a volume in R3. It's just, it is all of R3. The null space of A. What's a geometric description of the null space of A, Jorge?
It's a it's a 0.
It's the zero vector. Yep. Okay.
Point.
It is a point.
1D on
Yeah. What's that one?
It's
one dimension.
It's zero dimensional.
0-dimensional.
Yeah. It's zero dimensional. Points are zero dimensional. There's only one zero dimensional subspace, and it is the zero vector. Okay.
0.
Right. So it is a zero dimensional subspace of R3. Or you could just say it's a zero vector. It's the origin. Yeah, it's a point. But it's a point in R3. That is actually pretty important. That'll be more important in the next chapter. But it's a zero dimensional subspace of R3. Okay. What's the nullity of A then?
0.
It's 0. That's right. Remember that if the null space of A is the zero vector, the nullity of A is 0. This should also tell you, because what's the nullity of A? How do we define it?
Because it's linearly independent.
Okay, so that gives it, that's a relationship there between the vectors and the null space. But why is it that if the null space of A equals 0, that the nullity of A equals 0?
By the IMT?
Not exactly. It's even more closely related. All right.
I have
I4, that's the
the-
identity.
Because it's linearly independent. No. Okay. I don't know.
It's by definition. The nullity of A is the dimension of the null space. So if the dimension of the null space is 0, that means that the only thing in the null space is the 0 vector. Okay, so this is actually kind of really important. The nullity of A, right? Okay, is the dimension of the null space. And remember what I said, that there's only one way to get a 0-dimensional space. It's to have the 0 vector in it only. So the null space of A equals 0 means that null space of A is 0-dimensional. So that means that the nullity of A, or null of A as we write it, null of A equals 0. So yeah, they're all related. We want to get at like, well, why? And this helps us to understand what it means to be the nullity. The nullity of A is the dimension of the null space, right? How many vectors are in the null space? Well, if the 0 vector is in there, that's 0-dimensional. If the 0 vector is the only thing in there, it's 0-dimensional. Pardon me.
Professor, may I
Yeah.
ask?
Oh yeah. Go on.
So why is so for the null space it's the geometry of the null space is 0-dimensional subspace of R3 or R4.
It's of R3. And here's why. Because it's x1 equals 0, x2 equals 0, x3 equals 0. It's only got 3 components, so it's in R3.
Okay.
You see that?
Yeah.
Yeah. So you just form the vector and then count the components. It's got 1, 2, 3 components. It's in R3. All right. How's that, fool? I was going to do this, but I want to go and do some, and then confirm rank nullity of A. What's the rank of A?
Just using the
3.
rank of A plus the nullity of A.
That's it. Rank of A equals 3.
N equals 3.
Yep. Nullity of A equals 0. N equals 3.
3 equals 3.
Yep. So rank of A plus null of A equals 3 plus 0, which equals 3, which equals N. Done. All right. So very nicely done, everybody, though. I really like that. You guys did a very, very nice job there. Okay. So let's I want to take, okay, so I'm going to set up a set. So I'm going to let S equal, I'm going to set up this set. We're going to let S equal 1 plus 3x plus 2x squared. 3 plus 10x plus 5x squared, -2 minus 4x minus 6x squared, and 1 plus 6x minus x squared. All right, so that's our set. And my V equals P2R. So the first question is, are the vectors in S linearly independent? So we're going to ask ourselves, are the vectors in S linearly independent? So a basis for P2R, the standard basis for P2R is X, or 1x and x squared. That's the basis for P2R, 1x and x squared. Okay. So what is the dimension of P2R? What is then our dimension of P2R?
Is it 4-dimension?
Okay. Why do you say 4-dimensional?
Because the number of columns.
Ah, okay. Well, this is the number of vectors in the basis. We've got 4 vectors in the basis, but that doesn't make this like a basis for the vector space, right? It just
Yeah.
makes how big the set is.
Also, it's 3 because you have 3.
In the standard basis, we do have 3 vectors, 1x and x squared. Those are our 3 vectors.
Mhm.
So that makes the dimension of P2R equal to 3.
Okay.
Every basis for the space will have the same number of vectors, and that'll equal the dimension of the space. So in this case, right, we've got 3 vectors in the basis, so that means the dimension of P2R is 3. Okay. Now, how many vectors do I have in S? In my set S. My set S has how many vectors?
4.
It's got 4, right? Okay. So there are 4 vectors in the set. So are the vectors in S linearly independent?
No,
Why not?
because you have 3 and 4. You're missing 1
Okay.
set of vectors.
Kind of the other way around, everybody, right? Why is it? So like it does have to do with the fact that 1's 3, the dimension's 3, and the number of vectors is 4. What's the problem? What if I had 4 vectors in R3?
Then you know that one is linearly dependent.
Yeah, that one of the vectors makes the set linearly dependent because there's more vectors than dimension. What's going on here?
You
It's
have
the other
less.
way around.
Say again, what?
It's the other way around.
Meaning what?
You have I don't know how
This
to
is kind of the
explain.
tough part. You're like, okay, can I put that in my words? Yeah, go on one.
Yeah, I don't know how to say it.
All right, what's up, Daniel? Go ahead, tell me.
Well, going with the opposite of what we just said, they would be linearly independent since you have less vectors than dimensions.
Do we have less vectors than dimensions?
No, no. Wait,
Okay,
Um,
counting
Is it
still
gonna be-
works. Yeah, what's up, Con?
is it gonna be AX equal B doesn't, I mean, like has infinite solutions for it gonna do with
Well, I
that?
don't know that. I don't know that at all.
Ah.
All I'm asking is whether or not the set's linearly independent.
Sorry, can you say it again?
Is the set linearly independent? Is the set S linearly independent?
No.
Why not?
Is it because it's because we have more vector
Then what?
and a component?
Yeah, Jorge?
Is it because there won't be enough pivots? Like there'll be that
Well-
extra column and then that's where you get the free variable?
Okay. We are actually going to end up with a free variable in AX equals 0. That's true when we construct the matrix out of this. But we don't know that yet. Okay. We have more vectors than we have dimensions. I think people said it like a couple times and I'm like, okay, that's it, right? If you have more vectors than you have dimensions, right? P2R, there are more vectors than dimensions. So the set is linearly dependent.
Is it because the dimension is 3
Mhm.
and then
The number of vectors is 4.
number, yeah.
Yeah. It's like having, in fact, this is identical to having 4 vectors in R3. It takes 3 vectors to construct all of R3. So having a 4th vector makes the set linearly dependent. It's the same thing. In P2R, it takes 3 vectors, right? Like 1x and x squared to form P2R. Add a 4th vector and the set's linearly dependent. Same rules apply. Too many vectors. All right. Now we need to ask ourselves, does the set S span P2R? Now for this, we're actually going to have to go check. I mean, yes, you'd be like, oh, okay, well, it kind of looks like it. There's 4 of them. There's enough. But I don't know whether or not the set's actually going to span. Okay. So what I'm going to do is I'm going to transform these vectors into a matrix A. And we did that. We've done this before. So this is 1, 3, 2, right? So 1, that's the first component. 3 is the second. 2 is the third. And then we'll have 3, 10, 5, -2, -4, -6, and then 1, 6, -1, and that's A. Right? Can everybody make sure that you can do that? That's something that you may have to do on your exam. Because that's going to be how you're going to turn something into, turn a set of polynomials into a matrix. Okay? And then I'll write the RREF of A right here. The RREF of A is going to end up equaling 1, 0, -8, -8, 0, 1, 2, 3, 0, 0, 0, 0. That's my RREF. So here's the question. Does the set span P2R? Now that you look at it, does that set span P2R?
No, since P2R has 3 dimensions and here we only have 2 linearly independent vectors.
That's true. Yeah, so that's right. We don't have enough vectors. Absolutely. Can you guys see that? Only 2 pivots. So the span is going to be those 2. That's great. Anything else? How do any of you others think about it? Do you think about it the same way?
It doesn't span because it's linearly dependent.
Okay. That's not actually, those 2 in this case are not going to be related because the matrix isn't square. Okay, those are 2 different concepts. So in this case, we can't relate linear independence and span. These could potentially span, or the set could span. So we have a row of zeros, right? Remember, AX equals B is consistent is another way to think about this, the set spanning. That row of zeros tells me that the set will not span P2R.
Because it doesn't have a solution for all B.
That's right. Exactly. Because it does not have a solution for all B. That's right. Okay. So this thing down here, you can imagine that if we augmented with some B on this end, we could have no solution, right? No solution to AX equals B. And so hence no span. Does that make sense? Rows of zeros, no span. Okay. This goes with what Daniel was talking about. What is the span of S? So the span of S then is going to be, we're going to take the 2 pivots. All right. And we're going to go back to A. And we're going to select the ones that have pivots. So it's going to be the span of S is the span of 1, 3, 2, comma 3, 10, 5. Oh, excuse me, that's not true. We actually have to rewrite these as polynomials. So it's going to be these 2, but we're going to rewrite them as polynomials. So it's going to be 1 plus 3x plus 2x squared and 3 plus 10x plus 5x squared.
Professor, is it like, is this a call space?
That
Call
it is. It's the call space of A. The 2 are the same thing. The call space of A and the span of the column vectors is the same thing. That's how you define the call space of A. The call space of A is the span of the column vectors of A, which is the span of this set of vectors S. Does that make sense, Con?
Yes.
Yeah. Those definitions, they connect everything. So the better that you get at the definitions, the better things kind of connect. It's weird like that. You know, there's a lot of reading involved in linear algebra. All right. That's the span of S. What is the row space? Okay. So our next piece here is, what is the row space of A? Now we know with our definition of the row space, it's going to be the set of non-zero vectors in RREF of A. So it's going to be these first two rows, but I got to rewrite them as polynomials. So something to notice here is to notice that these are four-dimensional. There's four components. There's four components in the row vectors. So we're going to start just like we did before. We got, it's going to, one, it'll be span, because we're going to be looking at the span of something. And we'll start with, here's 1 plus 0x, I'll just write it, plus 0x minus 8x squared minus 8x cubed. And then 0 plus x plus 2x plus 3x squared plus 2x squared plus 3x cubed. You see that? So I just took the row vectors and turned them into polynomials. And that's my row space. Just in case if you haven't gotten to some of the homework questions that do this kind of stuff. It's really identical to everything else that you've done in terms of node space, row space, column space. The difference is, okay, is that you just have to turn it back into polynomials at the end. You just have to know how to read the polynomials. Worst comes to worst on the exam, write them in as vectors. It's a point or two off, but otherwise you know everything else that you need to know, which is important. Most important. Okay. And then we've got what is the null space of A. So we're going to solve AX equals 0. Right? And we'll use the RREF just like we've done before. But I'm not going to use the polynomials right now. I'm going to write it as x1 minus 8x3 minus 8x cubed, 8x3 minus 8x4 equals 0, right? And then x1 plus 2x3, or excuse me, x2 plus 2x3 plus 3x4 equals 0. And then we have two free variables. We have x3 is free and x4 is free. So x3 equals t and x3 equals s and x4 equals t. All right, just like we would find the null space any other way. So make sure that you can find the null space, and then we're going to turn into some vectors. So we get x1 equals, and then it'll be 8s plus 8t. x2 will equal negative 2s minus 3t. x3 equals s, and x4 equals t. So I need to write those as vectors now. So x, what we're going to get is x, my vector x, is going to equal s times 8, negative 2, 1, 0, plus t times 8, negative 3, 0, 1. And we're pulling those directly from our values for x1 through x4. So this vector and this vector, these two vectors, they are a basis for the null space. So you solve AX equals 0. Okay, and the reason why we're solving AX equals 0 is because that's what the null space is, right? It's the set of solid solutions to AX equals 0. This gives me the basis for the null space. And so because we're in P2R, I've got to translate. Okay, so I'm going to translate now, and that's going to give me 8 minus 2x plus x squared, comma, 8 minus 3 minus 3x plus x cubed. Excuse me. And then that is the null space of A. It equals the span of those two vectors. Questions?
I have a question, not regarding, when you're doing call space of just say A, do
Yeah.
you do equal to, and you put span in front of,
Uh-huh.
okay, yeah, thanks.
Or you can say a basis for this call space is blah, 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 blah. Right? And then just give me the vectors.
Got you, thank you.
No problem. Okay. So let's talk about the exam. First things first. Y'all have asked, okay, here's inside of the modules, there's something called Chapter 4, Topics and Terms. These are all the things that are expected to be covered, okay, in our exam, all right? For the most part, yeah, there it is. So write sets of vectors and set builder notation if you need to. Mostly you can just use that span notation. Write sets of vectors as linear combinations. So if you've solved a system, you know how to write it as scalar times a vector plus scalar times a vector equals the other vector, okay? Graph vectors, scalar multiples, and linear combinations. Do you need to be able to do that? You know what? For the exam, I'm not going to ask you to prove anything about subspaces other than determining the null space of a matrix. So you won't have to prove that something is a subspace. You just need to understand what a subspace is. You need to understand what the vector spaces are. But from 4.2 and 4.3, you'll just need to know how to find the null space. 3, span. All these things about span. Determine if a set of vectors spans a vector space. Determine the span of a set of vectors. We've done that a couple times today already. Determine if a vector is in the span of another set of vectors. Right? Can it be written as a linear combination of the set of vectors? 4, determine if a set of vectors is linearly independent or dependent. Booyah. Under all sets of conditions. Basis. Write a vector as a linear combination of the standard basis. That's pretty simple. We've done that several times. Write a vector as a linear combination of a given basis. You can use the change of basis matrix for that. Determine if a set of vectors is a basis. Determine the dimension of a basis. And then define the subspace of a basis, meaning the geometry of the basis. Is it a 2D subspace, 3D subspace, and of what space? 6, change a basis. Rewrite a vector in a new basis. to determine the change of basis matrix that transforms vectors in a basis C to a basis B. All right, that's very mechanical. I'm not asking you to like figure anything else out about it. Just form the change of basis matrix for B to C and C to B, and also rewrite a vector in a new basis. Row space, call space, and rank nullity. Determine the basis for a row space of a matrix. Determine the basis for the call space of a matrix. Determine the nullity of a matrix. Use the rank nullity theorem to draw conclusions. Basically, that's confirm rank nullity. Okay. Use corollary 4.93 and theorem 4.94 to draw conclusions about a matrix, system of equations, or set of vectors. And that's basically, you know, AX equals B has a unique solution. What does that say about the call space, right? Okay, what does that say about the null space? Or what about the null space and linear independence and dependence? We talked quite a bit about those. So make sure you look at those. And then the invertible matrix theorem. Prove or show a relationship between A through O of the invertible matrix theorem. So basically you just need to, you know, you're given a matrix or you're given information about a square matrix. You'll need to be able to tell me something else about that matrix, right? Just like we did earlier on in class. And use any of the statements in the invertible matrix theorem to make determinations about a matrix, set of vectors, or system of equations. That, right? If you want to go, what's the study guide? There it is. Other than the whole stuff about the vector spaces. Yep. This 1, 3, and 4 there, you won't have to do on the exam. Just something we did in the class. Now, in addition to that, inside of the module, we go back to the module. You'll see some, if you go to the chapter 4 exam page, just like in proof 4, you'll see some previous exams. I think, therefore I am. If we look here, like, and it's got rubrics for each one of them. Okay. I think very similar kinds of questions. You just may be asked to justify a little less. Okay, because yeah. Yep, there you go. Just depending. And so, like I said, be able to do all those things. You can utilize this in order to kind of study. You can see the kinds of questions that I ask. Okay. So like, suppose that the dimension of the call space of A equals 3, and the nullity of A equals 2, and the call space of A is a subspace of R4. What are the dimensions of A? Right? Okay. Maybe not even something like that. It might be even more straightforward than that. But yeah. And then you can look at the rubric. It goes along with those. I have office hours tomorrow from 1 o'clock to 3 o'clock. If you'd like to come in and talk, please send me an email. We'll set something up. And we can just find a time to go over anything here. In addition to that, what? If you have any questions, go ahead. Feel free to email me about anything. Okay. We can set a time. Like if you want to set up an appointment time, if you have like some issues or whatever, not issues, but more along the lines of like difficulties, or you need to get some questions answered, whatever, please feel free, send me an email. We can set something up. If you can't make the office hours from 1 to 3. All right. Okay. All right. Ask me anything. Now's your chance. You got 5 minutes. Not just about the math, but if you want to know anything about the exam. I may or may not be able to tell you. I don't know exactly. I haven't finished writing the whole thing. I'm kind of paring it down at the moment, actually.
Yes, the exam time.
It's 6 p.m. 6 o'clock to 8 p.m. and then you'll have 20 minutes to upload. All right. Well, good luck. Study hard. You guys do great. You're welcome. Have a great night.
Thank you for doing these little review sessions. They're really helpful. Same with the last one as well.
Thanks, Daniel. What did you think about the concept map?
Oh, that was nice. I love it. Yeah, because I was having a hard time trying to put it all together. So it's super helpful. It definitely was helpful going through these ones too.
Yes, some teaching innovation on this side worked. That makes me happy.
Thank you.
You're welcome.
Have a good weekend.
You too.
Have a good weekend, Professor.
You too.
See ya.